Okay, so this week we're going to talk about acids and bases again, but we're going to talk about them in more of a quantitative way rather than just a qualitative way, the way we did last week. So before we get started in this, I just want to introduce a term that probably many of you have heard called equilibrium. And so we're just going to give a very simple definition of this for our purposes. It just means that you have a system, so in this case we're talking about water, that is not changing, meaning in terms of concentration. So, for example, if you have a water molecule, it is being converted into H3O plus and O minus, and then the H3O plus and the O minus come interact together to go back and form water. Now in this case, we need to balance the equation. So here we need to put a 2, and we'll see the importance of that in just a minute. But so anyway, for what I'm trying to get across is that if we have equilibrium, that's about the only way you can ever talk about any system, and it just means that concentrations are staying the same. Okay, so if we're talking about the ionization of water, so water going to H3O plus and O minus, then what we can do is talk about the equilibrium constant. Okay, and so the way that you talk about the equilibrium constant in this case, we've got water written here on the left and the ions written on the right. So they're written in the place of the products. And so the equilibrium constant can be found by taking the concentration, so all this bracket means is concentration, and I'll explain that in a minute, of the products. So in this case, H3O plus and O minus are our products, and the starting material is water, because the starting material is always on the left. Okay? And yes, it's going back and forth, but for purposes of equilibrium, it's usually written where the ions are on the right and the neutral water is on the left. Okay, so if we write that out for this specific equation, then we have the equilibrium constant. So EQ stands for equilibrium. The K is the typical symbol for equilibrium constants, or any sort of constant. So we have our ions, so we have the concentration of the H3O plus and the concentration of the O minus multiplied together, and then all of that divided by the concentration of the water squared. And the reason it's squared is because we have to add a 2 here to get it balanced. Okay? So notice there's no superscript here, or the superscript is 1 in both of these cases, so we don't need to write it. All right, the concentration of a substance is usually in units of moles, we talked about that, per liter. And because we use moles per liter so often to describe solutions, it has its own term, and that's called molarity, and it's represented by a capital M. So in this case, we could rearrange this equation to be the equilibrium constant times the concentration of water squared, and that would be equal to the concentration of the 2 ions multiplied by each other. Now, for water, it turns out that the water molecules are, or the concentration of the neutral water molecule is so large relative to the ionization that it essentially stays constant. And so for convenience, we call this entire term here the KW, okay? And so the KW then, if we substitute that in for this, and you don't really need to understand that, but I'm just telling you where all this is going to come from, then the KW equals the concentration of the H3O plus times the OH minus. And so it is known that the KW equals 1 times 10 to the minus 14th, and then this has units of molarity squared, because this is in units of molarity, and this is in units of molarity. So this turns out to be in units of molarity squared. All right, so where am I going with all that? Why does that matter? What we're trying to understand is, if you remember in the pH, we had a pH scale that for water, goes from 0, or well, it can't even go into negative numbers, but it's up to 14, and then the neutral is 7. And so we never explained why pH of 7 is neutral. So where does that come from? Well, we're going to need this equation to explain that, okay? So when something is neutral, or when an aqueous solution is neutral, meaning water, What that means is the concentration of the two ions, so H3O plus and OH minus, are exactly equal. Okay, so those two concentrations, when they're equal, that means the water solution or the aqueous solution is neutral. Okay, so if you look back at that equation of this Kw, right, equals 1 times 10 to the minus 14th, when these two terms are equivalent to each other, right, then each of these must equal 1 times 10 to the minus 7th molar. Okay, that must be the concentration of each of those ions. Now the pH of any system is defined as the negative log of the concentration of H3O plus. Okay, so if we know that these two things are equal, then the concentration of H3O plus has to be 1 times 10 to the minus 7th. You plug that into the equation and the pH comes out to be 7. So that's why a neutral solution has a pH of 7. And so one more thing, and this is kind of beyond the scope of this course, but this Kw has a value at a certain temperature. Okay, so this value here is at about room temperature, and that can change, but we're not going to go so far into the discussion to worry about that. So we're just going to leave it there for now. But the important thing is that the concentration of H3O plus and the concentration of OH minus are equal to each other in a neutral solution. That's key. Okay. All right. Now, when you add an acid or a base, then what happens is, if you add an acid, then H3O plus increases. If you add a base, OH minus increases. Okay. So any disturbance of that equilibrium by the addition of an acid or a base will result in these two concentrations not being equal to each other. And then the pH will change from 7. If you add if you add an acid, you increase this, the pH goes below 7. If you add a base, you increase the concentration of OH minus, and therefore the pH goes above 7. Okay? So let's look at some problems that we could think about of how to actually calculate the pH. So if we added enough acid to an aqueous solution so that the concentration of H3O plus, and this should be a subscript, is equal to 0.010 molar. So remember, here we have two significant figures because this 0 is a significant figure, this one and this one are not. They're just placeholders. What's the pH of the solution? All right, so how do we find that? Well, so this is just reminding you that if you wanted to write this in scientific notation, we have two significant figures, so you would write 1.0, there's our two significant figures, and then times 10 to the minus 2. So, and I get that from just moving this decimal place, 1, 2. And because I'm moving it to the right, this number is negative. All right, so let's plug it into the equation. pH equals the negative log of the concentration of H3O plus. So that's pH equals negative log of 0.01. And that turns out to be negative 2. So now we have the pH equals to the negative 2, which means the pH is 2. And that's what you'd expect because this number is much larger than 1 times 10 to the negative 7th. So it better be lower than 7. All right, now what if the concentration of H3O plus is 0.0003 molar? Again, we have two significant figures. What's the pH of the solution? We can rewrite this if we want to more clearly show that it's two significant figures by writing 3.0 times 10 to the negative 4th. And again, that should be in molar. Okay, so the pH of the solution then is, if you take the log of this on your calculator, so in your calculator what you want to do is type in this number, take the log of it, and then change the sign. So don't type in the negative before you take the log. So in other words, we're taking the log of a positive number. And when you do that, you get negative 3.5. So now it's negative 3.5, which is 3.5. And again, you'd expect it to be an acidic pH because this concentration is, again, much larger than 1 times 10 to the negative 7th. All right, but what about going the other way? So you could be given the pH of the solution and asked to calculate the concentration of H3O plus. Okay, And now, if the pH is above 7, then the concentration of H3O plus is going to be less than 1 times 10 to the negative 7th. Okay, because this pH means that OH minus is greater than the concentration of H3O plus. All right, so again, we're doing the pH equals to the negative log of the concentration of H3O plus. So now we plug in 8.2 for pH, and then it equals to the negative log of that. So if we want to solve that, we're going to take out the multiply each side by -1. So then you get negative 8.2 times the positive log of the concentration. And when you type that in, if you hit negative 8.2 and then hit if you have a scientific calculator, you can hit 10, should be something like 10 to the X button. Normally that's what it looks like. Then what you find is the concentration of H3O plus is 6.3 times 10 to the negative 9th. So notice that this number is smaller than 1 times 10 to the negative 7th. Okay, and it should be. That's what we were predicting. And then down here I just have a reminder to you that the concentration of H3O plus is less than 1 times 10 to the negative 7th for a basic pH, meaning above 7, and more than 1 times 10 to the negative 7th for acidic pH. Okay? All right, so you have some problems now that you can look on your worksheet, and you can review the math in this video and make sure that you plug in these numbers into your calculator, and you can get the same thing I do. I've given you a couple of different ones, so you can try that out, and then you can solve the ones on the worksheet. Okay? Good luck.